Good afternoon and welcome to my presentation. So today I am going to present on spinel nanoferrites, and the title of my presentation is Emerging Spinel Nanoferrites Toward Advanced Electronic and Functional Device Application. So my name is here presented by Dr. M. D. Sarwar Hussain, Assistant Professor, Department of Physics. So first of all, I am showing the outline of my discussion of today. So in the beginning, I will discuss about the historical background of spinel nanoferrites. Then I will show what is spinel nanoferrite. Then why spinel nanoferrites. Thereafter, sample preparation of spinel root. Then structure and microstructure of this type of materials, dielectric properties in the frequency domain, magnetodielectric properties, that is actually magnetodielectric coupling for our applications. Then I will show some application and achievements and future aspects for our students. Last of all, I will show my some publications of this year. So let me start with the history of spinel nanoferrites. So spinel word is a very interesting word. It came from the Latin word that is spinel, that is meaning little thorn or spine. In Bengali, it is called actually kata. So it was invented more than 2000 years ago. So near about our country, from Sri Lanka, Myanmar and northeast Afghanistan. That time it was very much popular as a gemstone materials. That composition was MgAl2O4, that is, and the minerals are looking like that. Different region of country with this was found from actually Sri Lanka, northern Afghanistan, Myanmar, and from Vietnam also. And actually it was included scientifically in the late of 18th century for its huge application. So what is spinel nanoferrite? So spinel nanoferrite is a class of magnesium aluminate, that is MgAl2O4, having general formula of this Mg. So, Assalamu alaikum, Din sir, being presented here. So here actually I am going to show what is spinel nanoferrite. Spinel nanoferrite actually includes some iron atom there. So the composition is following the MgAl2O4. Here the compositional is showing here Mfe2O4, where the M is the divalent metallic ion that is included here, and here is the unit cell structure. So this sample nickel ferrite, and this is the powder form that we made inside our lab, and this is the ceramic nickel NiFe2O4 ceramic form when after the heat treatment was performed, and the unit cell actually of this nanoferrite is like this, where there are two sides. One is tetrahedral, another one is octahedral. So octahedral side, here is octahedral side and here is tetrahedral side. Tetrahedral side contains the, it is called the A side, where actually the divalent atom cobalt 2 plus, nickel 2 plus, zinc 2 plus, manganese 2 plus. This type of element can reside in this side, tetrahedral side. And octahedral side, it contains like iron element there, it can reside there. So after that, I found that there are three types of spinel. One is normal, one is inverse, another one is mixed. So that the key properties of this material is high magnetic permeability, and saturation magnetization, good chemical stability, low eddy current losses, and tunable electric and magnetic properties via doping. So here, the normal spinel structure is like that, where magnesium takes place at the tetrahedral site, and at the octahedral site the trivalent atom aluminum 3 plus takes place, and oxygen are surrounding with this material, with these sides actually, and here it is showing the tetrahedral site A2 plus and B3 plus B3 plus, that is at the octahedral site, and O4 here. This is a normal structure. It is an ideal structure, we can tell, but actually whenever we are making this sample in laboratory, this type of structure generally is not found. So that I would to explain the inverse spinel there, where actually one element from the octahedral side, it is replaced to the tetrahedral side, that is B3 plus, and for spinel nanoferrite it is actually Fe3 plus iron. From octahedral side, one iron whenever shifted to the tetrahedral side, and from the tetrahedral side the divalent atom it shifted to the octahedral side, then we call it inverse spinel. And it's also depend on the chemical stability whenever we are making the samples. So it is also we have to note down. And this structure we are showing here, actually this sample we made, and we found it is inverse spinel. After that, I am showing some mixed spinel. Actually, whenever we discuss about the structure of these materials, or based on this structure, the whole properties, whole applications depend on this structure. So sometimes it is confusing whenever we are publishing articles. Reviewer is asking questions whether the materials is inverse spinel or mixed spinel or general spinel, normal spinel. So some paper is reporting that it is normal spinel. I am confidently sure that whenever we are making these materials, normal spinel would not be found. Either it is inverse spinel or mixed spinel. So here I am including the mixed spinel. What is happened there? Actually, some atom, all atoms are at the all sides. Here is divalent, trivalent tetrahedral side, and divalent, trivalent is octahedral side. This sample also we made. This is nickel ferrite. Here also we reported in an article that our sample we made, this is mixed spinel ferrite. Now interestingly, how we get this? I will include this findings, how to determine this. This will help to the CSE student who can do some simulation method. So now, why spinel nanoferrite? I will tell. Versatile spinel structure, I have already discussed. The diverse cationic distribution and tunable magnetic and electrical properties, because we can tune this. After that, excellent magnetic properties. These materials show the ferrimagnetism and size dependent magnetic behavior, because whenever we make this sample, the grain size actually varies, micro to nano. So depending on this grain size, its magnetic property also varies, which is this time we need for biomedical application. I will also show that. After that, the wide range of applications, microwave, spintronics, this type of applications lot of happened previously. Energy storage, it also lot of happened. So sensors, catalyst, it also more articles on this side. Biomedical uses, drug delivery, MRI contrast, hyperthermia. We included the hyperthermia. This is more challenging job. We are focusing on that with the help of Biomedical Center, Research Center of our AIB, and also energy storage we also trying, but main focus is we are trying to make an antenna that will work for low frequency communication. Last of all, the high thermal and chemical stability. Actually, more than 2000 years ago, the king used to make crown using this type of gemstone spinel mineral. They did not know that time why it is long lasting or why it is looking very nice. Actually, this type of spinel composition has high thermal and chemical stability. It is long lasting materials. For this reason also we are making in laboratory. This is also very much important because it has a high thermal stability and high thermal and chemical stability. So these materials can be used for a long lasting purpose. So I am showing here a route of sample preparation whenever we wish to make a nanoparticle or nano level sample. So starting from this type of raw materials, I have shown here an example how to make a Spinel nanoferrites or nano level materials by using the method. This method is called sol gel method. This type of instrument is available in the CNL lab. We can make it at any time. Student, you can make it inside our lab. So we can start from the nitrate as a raw materials. Then we have to include some deionized water, and using the stirrer we have to perform 30 minutes of stirring. Then dropwise we have to mix citric acid inside that solution. Then heating and stirring up to 70 to 75 degrees Celsius with a magnetic stirrer for 8 to 10 hours to get the red solution. After that, we have to include ethylene glycol to keep the pH at 7. Thereafter, the solution is to be heated 70 to 75 degrees Celsius to initiate the polymerization reaction to get the gel. This gel will be dried at 100 degrees Celsius for 24 hours. Then we get actually a fluffy type powder that is zerosol, that is named zerosol, and we have to grind it, and we have to apply some heat treatment to improve the quality of crystallization. That is 600 degrees Celsius is enough for making crystalline for 2 hours, and finally we can get the nanoparticles of spinel. So it depends on whatever we wish to make, whatever composition we wish to make. This process we can make the nanoparticles. But what happened in this method? We did not get more enough sample for our device fabrication or integrate to our device for our actual purpose. So we followed some other routes, that is cost effective and very easy method. That is actually solid state reaction method. We implemented double sintering technique. One is pre-sintering, then after the final sintering. So here the raw materials are the oxide materials, and these oxide materials we did 4 hours of dry mixing by AZ motor. After that we made a pelletization. This actually we took help from other source, but next future we also have inside our lab. So after making pelletization, we perform the pre-sintering. This is preliminary sintering. That means we will apply some heat preliminary at 10 degrees Celsius per minute and kept it inside furnace for 2 hours, 800 degrees Celsius. Then the furnace cooling method. Then again we ground that pellet, again grounding for 4 hours, 4 to 5 hours. Then again pressing to the desired shape, pellet shape. Actually we make two types of samples. One is toroid shape, one is pellet shape, because this toroid shape will measure the permeability of the materials. We can measure the permeability and magnetic permeability, and another one we measure the dielectric constant. So in the meantime, we performed another sintering process, that is the final sintering. Holding time is 6 hours. Heating rate is 15 degrees Celsius per minute, and the final temperature. This needs actually more temperature, high temperature for making this method solid state reaction. That is 1332 degrees Celsius. And after polishing and cleaning by ultrasonic bath, we got this type of materials. I am showing an example of this type of materials. We made the solid state reaction method, that is chromium of ferrite materials. This is one of the challenging materials nowadays, this time, because I got only 4 articles on it, and people are not reporting on this article because this is non-magnetic. This is showing non-magnetic property, and this is not this can store charges, but this cannot applicable for communication device. So I took a challenge for improving these materials. Okay. So primarily I found the structure of it as a mixed spinel here. It is showing, it is confirming me mixed spinel structure. But how I got this? So here I think CSC student are here, computer science student. So you can use the foolproof software, that is by read-belt refinement and cationic, some cationic distribution where the atom seat there. Then here you see the data, the red color dot is the experimental data and the black line are the simulated data. This simulated data came from the equation, and the the blue color line is showing the difference between the red dot and the simulated calculated black line. This ensures that how much your simulation is perfect. After performing this, you will get this type of structure, whether the materials is mixed spinel or inverse spinel or general spinel, normal spinel. We confirm that more things also if you can find from this, that is cationic distribution. The iron is displaced from A side to B side. Actually this materials is like a window. You are going outside and you are coming from outside. You can control this by doping. So here also we control that iron from A side shifted to the B side. And also here it is found that some of the B side iron shifted to the A side. And this shifting actually improve or enhance the magnetic property. So I am showing here grain size. These particles actually the microstructure is showing we have improved the sample grain size. How we improved? Because whenever we doped the materials and heat treatment, the size of the materials is decreasing, and we have reached to the 500 nanometer up to, and hopefully we will reach to the nano level. Acha, before going to the magnetic property, this part is for the EEE students. How we can measure the dielectric constant, and what is the dielectric constant? Dielectric constant actually show us that the stored capacity of the materials, or how much charge a material can store. How can we measure this? We prepared this type of materials, ceramic pellet shaped sample. So by using the formula of parallel plate capacitor, we can measure the capacitance of this material. I think in physics 1 course you have learned these things. Physics 1 course we have shown you that how parallel plate capacitor we can measure. So this is the equation, and we can make this type of connection both sides of the samples. This is our sample. By silver pasting and connecting copper wire, these two wire can be connected to the LCR meter or with an impedance analyzer. This is a very easy experiment. You can measure the dielectric constant, and from the dielectric constant we find two parts. One is real part, another one is imaginary part. Real part actually show us the energy stored inside the materials, and the imaginary part will show us how much energy is lost inside the materials. This is also important for application, because you are applying energy but energy is losing. So this part is also important. We have to focus how much is losing, and we have to count it. Finally, stored energy we can calculate from this formula, U is equal to half CV square, where actually C we can measure by the parallel plate capacitor method. This is very much easy experiment. Then we have measured this, and we found that our dielectric constant actually decreasing. Black one is our undoped sample, and whenever we implemented our doping there, cobalt atom we implemented, dielectric constant continuously decreases, and finally found that this material actually is not good for storage energy. It will not store energy, because at first I told that my target is to make a sample for communication, so that I confirm there, but the dielectric loss is also in decreasing here. Dielectric loss is also very few. So that it is perfect for application but not for energy storage, for communication. How I confirm that? From here, this is my actual result for amplification in the device. That is, first of all, I enhance the magnetic property. Chromium ferrite is non-magnetic, but now see, whenever we doped cobalt inside the materials at the site of the chromium, then the magnetic permeability increased, and also magnetic hysteresis, magnetic saturation also increased. And here it is showing the loss factor, the amount of loss. Here is written indicates the magnetic energy loss as heat. This is also indicating that whenever we apply some magnetic field inside the materials, it will generate some heat because of dipole magnetic domain polarization. It will show some rotation of spin, resonance of the rotation, and this frequency confirm that if we apply some magnetic field of around 48 kilohertz or 51.5 kilohertz, that is AC magnetic field, it will generate some heat. Like induction, it can generate some heat, these materials. So this is my core finding. And finally, I am successful to make a good matching impedance between magnetic and dielectric property. That is the steady a bandwidth is showing there, a steady of 2 megahertz bandwidth, and from 1 kilohertz to actually approximately 10 megahertz. In this frequency range, it can work for a communication device because the matching impedance means the magnetic and dielectric coupling, that is showing from this coupling the result of ratio between the impedance of the materials and impedance of the air. The ratio between these things is near about 1, but we did not succeed to reach exact 1, but we are reaching to the nearest about the 1, that is 0.8. It is nearer to the 0.8, and we need more doping. Work is going on, and we are making the nano level. So hopefully we will reach to the 1 and a broader frequency range, and it will also work as for a communication. And finally, our destination reaches to the communication system, and a 3 model I am showing here. One 3 model that is here showing if we make this type of ceramic materials inside a box, we feed it and it will work, and with the connection of RF signals, it will work for miniaturization or communication system. Our materials is here, that this color, chromium doped cobalt ferrite, we can fix there our materials. This part is for communication device. My 3 students is working inside the lab for successfully work this type of things. Another one is biomedical application. I told that these materials will function for generating some heat to kill a cell that is cancerous. Cancer cell is, suppose it needs to kill 40 to 44 degrees Celsius temperature, and also indirect way we calculated that if we apply this type of frequency 51.5 kilohertz AC magnetic field, if we apply, it can successfully destroy this cell without any making harm inside the body, and it will generate 40 to 44. It 40 to 44 degrees Celsius of temperature it can generate, and from this graph we confirm. Now we need to implement. We are waiting for the implement. These are the achievements. Previously we succeed to for the magnetodielectric coupling, but it reaches more than 1, and it is not stable. We did not found stable, but stable matching impedance we found for chromium ferrite, cobalt doped chromium ferrite. This is another success, our nickel ferrite that is doped by zinc and vanadium. We found that this is applicable for spintronics application. This is the latest work. Last work we did, we implemented as a multi-layer ceramic capacitor. This also we are making inside our lab. This is the future aspects: enhanced functional design, nanostructuring and size controlling. We have to control the size for more efficient materials. Device integration, this work is going on actually. And biomedical and energy application, this is also going on. So who are interested, you can join with us. Computational and theoretical studies, this site is for CC students who are interested, we can teach them. Collaborating and scale up, it is continuously going on. So these are the publications on Spinel ferrite this year, and 5 of them I directly corresponded in this work, and all the theory goes from me. We started work from 2024. Our previously prepared sample. In 2024, we are preparing some sample, and also students are included here. And currently, we are doing work here. 3 of the students, they have also made a circuit there, which will be connected with our materials. And our respected Rabanisar is here. He is searching for new things inside the materials. And also here is the biomedical application related work is going on. So we are doing work at the 2 domains. One is biomedical, another one is electronic applications. And the main focus is producing nano type work. So there are 2 projects currently going on: microstructure based magnetodielectric tuning at nanoscale for communication and energy storage devices. We are trying to prepare some sample at the nano scale. Here is another project that is funded by AIUB, enhancement of anti-cancer activity of barium titanate reinforced by zinc, strontium and molybdenum doping, along with biomedical and energy storage device application funded by AIUB. And these are the members in this project. Me, our respected head madam, Jyotish sir, Dr. Jyotish sir and Tushar. And first project, I am also working as a project investigator, and Rabbani sir as a co-PI. These 2 works currently going on. So thank you for being with me and listening. So is there any suggestions, or we can discuss? Any questions or?
Thank you, Dr. Sarwar. For the communication device, have you established any range, that how much range it would cover? Have you done something on that?
First of all, actually we are trying to catch signal between the frequency range 1 kilohertz to 10 megahertz, and just the circuit part we developed, but we are at the midway actually the work, and success did not come, but from the research level we are very much sure these materials will work, but range we did not measure yet.
Thank you, Dr. Sarwar sir. Wonderful presentation. And it's a little bit complicated to understand within this short time. I think many information is there. However, I would like to know that if you incorporate some other nanocomposite to your ferrite material, is there any new opportunity or new dimension can you see? Is there any prospect?
If we go to nano level.
You are actually going to nano level, but if you incorporate other nanocomposite like gold, copper,
Yes.
incorporate. So, is there any possibility? Have you thought about it?
Yes, whenever we implemented gold, then our materials turn to the better for the energy stress. I have shown already, but it depends on whatever you wish to. Because spinel nanoferrite is such a material. Whatever you wish to make, whatever you try to apply, so you can tune it. Either if you wish to tune magnetic property, you can tune it by doping elements. If you wish to improve its dielectric part, you can tune it by other materials like yttrium. You can include some other materials you can include, and this depends on the doping and cationic distribution. Cationic distribution is the major part of tuning these materials.
So, you said the bivalent cation is widely used. So, is there any other cation, trivalent or tetravalent cation? Can be used?
Tetravalent we did not try actually, but trivalent and divalent we tried. Versatile materials we tried.
Awesome. Tetravalent is not widely used, right?
No, tetravalent.
So now I would like to know the particle size which is giving the enhanced properties. Which particle size you have got the more enhanced properties?
Okay, it depends on the actually surface to volume ratio and whatever properties you are expecting. If you enhance the magnetic property, you need the particles of nano level. Okay, so approximately 100 to 200 nanometer is very much good. And but for if you wish to use some dielectric applications, or if you wish to like our this depends on the actually composition and the size of the grain size, and also depends on the porosity. The inside in between the grains, how much porosity is there. Because porosity acts as a demagnetization, so that nanoparticle is the nano means 100 to 200 nanometer range particle is good for magnetization, but it should be controlled for application. Very much high magnetic field does not work for communication, and very much high magnetic field does not work for hyperthermia, because you could not apply AC magnetic field for domain alignment and produce some heat. It will not, the domain will not align like that.
Thank you.
Sorry for interrupting you. VC sir will join another program, that's why we want to hear him before finishing question and answer session. Sir, would you please come to the stage? Question and answer session will be continued.
Bismillahirrahmanirrahim. Honorable Acting Dean of the Faculty of Science and Technology, the Head of the Chemistry Department, and the Director of the Center for Nanotechnical Technology Research, CNR, and the speaker of today's seminar, the audience, the faculty members, ladies and gentlemen, Assalamu alaikum, and a very good afternoon. It's a very good effort that you are giving, that you are doing some research work and coming for a presentation. And this will be continued, this will be continuing in the days to come. Important thing is that his topic is pretty complicated, isn't it?